Hi, and welcome to this video, which is the overview to the EASY-HAZ laser hazard analysis software. The first thing is I'm assuming that you were able to get through the getting started video and you have the software up and running and you're sitting on this first page, which is the interface page. This video is really about just getting a bit familiar with the software, how it's laid out, a few parts of it, where the menus are, and we'll just briefly go through each section with the idea that in follow-up videos you'll be able to look at each section of the software in detail, where we'll discuss not only that section but we'll be sort of working hazard analysis so you can see how that section works while you're doing a hazard analysis. So with that, we'll get started. EASY-HAZ is just a workbook, an Excel workbook. It has two sheets to it, or 2 pages. This is the interface page. This is the tab for it, EASY-HAZ. We also have a database, PDB, which stands for Personal Database. Not too creative, but that is the name, the Personal Database, or the PDB. Click this tab right here, and we can get to the interface page, to the PDB. Both the PDB interface and the EASY-HAZ interface have menus associated with it that interact with it. You'll find those menus in the add-ins. Click the add-in, you'll see the EASY-HAZ PDB label. Click that and you get the various options in the menu. The menu bar up here is for Excel, although some of them will certainly work with EASY-HAZ. EASY-HAZ is really standalone in terms of needing those menus, so you don't do anything with those menus and interact with EASY-HAZ. The only interaction you have from a menu are these pull-down menus that do work and interact with EASY-HAZ. Let's go back to the interface page. We'll come up here to add-ins, EASY-HAZ, and you can see here are the options for the interface page menu items. As we said before, the one thing I do want to point out again is if you click the file and do a save, nothing's going to happen in EASY-HAZ. It does not save any of the parameters or anything you're working on. As I said before, the only thing that interacts with this are in the EASY-HAZ menus. So let's start all of this by taking a look at the menus. This is where we save our input files. So if we're working on an analysis and we want to save that to a file to hold on to it, then we'll save it to file. We can also start a database. For example, if you're working on multiple analysis from a single area or a single lab, and you may want to group them together, this is a good place to do it, is in the PDB. You also can select it both, so what it'll do is it brings up a dialog box for you to name the file and where to save it, and at the same time automatically ports it off to the PDB too. But we'll be looking at that in detail later. If you've saved your input parameters to a file, then you can load them back in using load parameters from file. This just brings up a dialog box which asks you to go find the file, and then it loads it in. If you want to do a quick save, in other words, you don't want to say, you're not going to take the time to name anything. You just want to hold on to the parameters for a bit. Maybe you're going to change some parameters and you want to get back to your base parameters, or you're going off to lunch or ending the day and you just want to do a quick save. That's what these are for, quick save. And if you have EASY-HAZ version 2.0, these are called save parameters to default files and load parameters to default files. Thought it would be a little more intuitive. We've changed the name, and so we've changed it to quick save and quick load. Obviously, you can quick save 5 files and then, of course, load them in quickly by doing the quick loads. Right here is where you generate the report. If you're going to do a report, simply click this and come out here and click Hazard Analysis Report. EASY-HAZ reaches out to the Report Forms folder, which has to be in the same location as the EASY-HAZ workbook and software. It picks out the template it needs and puts out all the information, your inputs and outputs, out to the report. We then look at extended features. This is where we set EASY-HAZ up for doing an extended source analysis, both surface emitters and image sources. And then this selection is for optically aided viewing, where we can change the limiting aperture, the transmission through the optics, the magnification. And we'll talk about all of these later on. these two particular, when we're talking about extended sources, needs quite a bit of discussion. We'll talk about those more in the detailed section when we get to the intrabeam section, which is right in here. So that's a little bit down the road. We're not going to take any of that on right now. Optically aided viewing, we'll talk about that when we get to optical considerations, and we're toggling optically aided viewing on and off. We'll take a look at this menu option here. We have some miscellaneous features, lens on laser. If we click that, you'll notice that this box changes so we can see some different information. Again, we'll talk about this at another time in detail. Let's go back and look at miscellaneous. We'll set that back to the correction factors and time limits. Interpolated transmittance calculator and OD transmittance calculator. This is just something that allows you to, if you have filter data, to interpolate between two wavelength values to get an OD or a transmittance. And the OD transmittance calculator is if you have an OD or you have a transmittance and you want to know what the other is, that's what that calculator does. We'll look at that in more detail later. Navigation, this is just if for any reason you lose these tabs, you always have these navigations to go back and forth between the interface page and the PDB interface page. You can get to the Kintec homepage and also the FAA homepage. If you're using EASY-HAZ to work with lasers outside and you want some information from the FAA, you can hit here. It'll take you to the homepage for more information about doing laser hazard analysis outdoors and what you have to do to report to the FAA. Show scroll bars and hide scroll bars. This is if you're, for any reason you lose these scroll bars, or when you first bring EASY-HAZ up, they're not here and you need them on, you can access the scroll bars here without going up here to the file and then options and trying to find how to turn the scroll bars on. Sometimes the scroll bars may go off if you bring up another workbook and you're switching back and forth. So just put that in to make it a little easier. Restart EASY-HAZ if at any time you think EASY-HAZ isn't running correctly. And one of the ways you can tell that is you'll notice that the only time you can click into a cell are these yellow cells, these input cells. These lighter cells are the blue cells you can't click into. If you do, it just takes you back. If at any time you see that you click in here and it stays, that means that EASY-HAZ may not be running it correctly, and instead of shutting it down and closing it and bringing it back up, which is actually very easy to do, you can just come in here and hit restart. The thing I will remind you is that the restart typically will wipe out some of the values you have in, so it's always a good idea to be saving your work. And then of course you have about, which is, it just tells us what the version is and the software, the Kintec Corporation and their website. Here we have the laser source information. This is where you have data description. This will give you, if you click the data description block, this brings up a form which allows you to input a lot more information, and when you save off the analysis to a file or to the PDB, this work is saved also, and if you put anything in the report notes, it appends that to the report when you generate a report. We'll talk about that. There's quite a bit to talk about in this later on, but we'll do that when we discuss this section. Wavelength units, nanometers, and microns is what we work in. It's up to you as to what you would prefer to do. I will say that when you select either one of these, it affects this fiber optic section down here primarily or not primarily, only for the single mode fiber where it says mode fill diameter. If you're in nanometers, it'll tell you it's looking for the mode fill diameter in nanometers, and of course in microns, it puts it in microns, and we'll talk about that a little later. Your wavelength unit is here. In the ANSI standard, this software is based on the ANSI Z136.1 2022 standard, and the wavelengths we work with are 180 nanometers to 1,000 microns or 1,000,000 nanometers. In this section, mode of operation, you can click, we have 4 modes of operation. You can see what they are here. We'll talk about each one of these in more detail. They do affect what shows up here, depending on what we select in continuous mode. Obviously, you get average power. We do put energy in here, but you'll seldom use it because energy, when it comes to continuous wave, means the total amount of energy. But depending on what you select here, you'll select either some form of power or energy, and then you'll input the value here. Pulse duration if it applies, repetition rate. The ANSI default exposure duration, this is driven when you have this up. Anytime you change the wavelength, it will automatically select the ANSI default exposure duration for an accidental or unintentional exposure. Okay, I'm going to give you a quick example of that. If we put 532 in, visible, it selects a quarter of a second. If we put a near IR in, it'll go to 10 seconds. Anytime you see these blue cells in the description or the label cells, if you click it, something will change. And let me show you what that is. For example, if you were working with multiple beams and let me say that better, multiple wavelengths, not multiple beams. You have a single beam with multiple wavelengths in it, and maybe some of them are visible, mixed with near IR, and we don't want the exposure duration to change if we're switching back and forth and looking at different wavelengths. Okay, so what we can do is click this off, and you'll notice now when we go to 532, nothing changes. So that's all that is. It just when you see a blue cell, it allows you to switch something on or off or change how that input is taken in. If we're running pulse groups, then we'll have group duration and group rep rate here. We have optically aided viewing, and we turn it on and off depending on the wavelength. Atmospheric attenuation, this is a value you put in if you're looking at an analysis for a laser that you're working with outside, and you don't want to, obviously the software assumes you're in a vacuum right now, and if you say, well, I've got, I have a standard clear day, well, you can put the atmospheric attenuation value in for a standard clear day. We do have information, a graph for looking up what those values are depending on the quality of the day. That'll be in the folder with the software as we're putting this stuff together. Here's where you get this ocular MPE is the MPE that the software will be working with to do calculations, for example, the OD and NOHD. We say this is the one, the MPE it's using, because depending on what you select, for example, if it's repetitive pulse or pulse groups, you'll get a lot of different MPEs involved. You can, for a repetitive pulse laser, you can possibly have up to 3 MPEs, and we have to do an analysis with each one to determine which is the most restrictive, and then that's the MPE that's used. For pulse groups, there can be up to 6 MPEs, but right here's where you'll want to look to see which MPE it is using to do its calculations. If you click here, it'll give you the AEL. Here's the skin MPE and the times skin MPE. Since we don't report anything like an OD value, you may not know immediately, well, do I have a skin hazard or not? So this times skin MPE becomes pretty important in the fact that if the times skin MPE is 1 or less than 1, you don't have a hazard. If it's above 1, you have a hazard. Now, to the extent of to what extent the hazard is, and what I may want to do to mitigate that hazard depends on how far above the MPE you really are. In other words, if you're only 2 times above the MPE, it's probably not. You just want to caution users about it. If it's 100 times above the skin MPE, you want to make sure people don't stick their hands in the beam, something like that, because, yeah, that'll hurt. But that is a self-correcting action. Do it once, you probably won't do it again. Okay, you have this section, which is the intrabeam. Now, you'll notice we have the intrabeam section, lens on laser, fiber optic, and diffuse reflection. Remember, this software is patterned after the ANSI standard. The ANSI standard talks about, for example, if you look at the formulas, the intrabeam NOHD, the lens on laser NOHD, the fiber optic NOHD, the OD for diffuse reflection, and so that's the reason we have these sections. These three sections are really sort of the same thing. Okay, we'll talk about that at a later time. But for the intrabeam, we can select whether it's in 1 over E squared or 1 over E. Of course, in safety, we always work in 1 over E, but most laser manufacturers give their beam parameters in 1 over E squared. If you input in 1 over E squared, the software automatically converts that to 1 over E and begins doing the calculation. For the spatial profile, elliptical Gaussian, circular Gaussian, elliptical top hat, and rectangular top hat. Those are the 4 most common profiles, and you can certainly do any safety calculation with these. Circular Gaussian will give you the worst case result. Elliptical top hat is the less restrictive result. All right, here we have the major axis diameter, minor axis diameter, divergence, and divergence for a major and minor axis, and the m² limits. The major axis diameter, all beam propagation equations pretty much assume that you're working from the beam waist. So when you enter the beam diameter, the software is assuming that is from a beam waist, and that the divergence for that, the divergence you enter is the associated divergence with the beam coming out of that beam waist. Okay, m² is another propagation factor. Some people call it a beam quality factor, but it's really a beam propagation factor. If you know either the diameter or the divergence, and you don't know, you know one but not both, but you know the m² value, you can put m² in, and it will calculate what the corresponding value is based on which one you have and that m² limit. If you don't know, if you only have the diameter or you only have the divergence, put an m² of 1 in. That's the theoretical limit. That's the best you can do. That is for a perfect Gaussian TEM00 beam. We put 1 in, and it'll calculate what the minimum beam diameter is for a divergence, or it'll calculate what the minimum divergence is for a given beam diameter. Okay. Observer range, this is where we want the analysis to focus on. Where is our observer standing within this beam? So it may be that, well, the closest my observer can get to any part of this beam is 1 meter. So, and say that's 1 meter from the output aperture. So I'll put 1 meter in there. We typically never do an analysis closer than about 10 centimeters. Also given here is a result. Once we put beam information in and we locate our observer, we'll get the beam diameter, major and minor, at the observer distance. Then of course we report the OD calculated at the observer range. We also report the worst case OD. Remember that in laser hazard analysis, we work with limiting apertures. The worst case assumes that all the power is passing through the limiting aperture, whereas if we have a large beam passing through a smaller limiting aperture, that limits the amount of power through the limiting aperture. And of course, the OD at observer range is calculated based on the power passing through the limiting aperture. We then report the nominal ocular hazard distance for the eye, the NOHD. If we click here, we get the skin nominal skin hazard distance, or the NSHD. Let me back up for a second. Sometimes you may not want to use m². I forgot to mention this. When we're dealing with a laser beam and we're working with m² and we give the parameter, the beam diameter at the beam waist parameter, we begin propagating the beam out of the beam waist according to a hyperbolic function. Okay, but if we're doing something like a surface emitting diode or an LED or a diffuser, for example, an engineered diffuser, we often, the spec is that the light is being put out in an angle. So let's say, 250 milliradians. But we don't want to calculate that using a hyperbolic function. We just want to go straight into that angle. The way we do that is turn m² off. And then it propagates the beam just straight into the angle instead of using a hyperbolic function. Also, you can turn this off if you're given beam information for a diameter and divergence, and the software comes back and says you're trying to exceed the theoretical limit of m squared. If you still want to proceed, then you'd want to click m squared off. Okay. In optical configurations, we have lens on laser and fiber optic. It's pretty straightforward. This is the focal length of the lens. This is normally used when we're looking at industrial lasers where we have a beam going through a focusing lens. We're focusing down to a point, and then what we want to know is what is the nominal ocular hazard distance from that focal point on out, and that's what this section does. So we give the focal length, you can give the beam profile, the major or minor axis diameter. Of course, we also have the observer range, where we want the observer placed for doing the lens on laser analysis. Then we give the OD at observer range and the lens on laser in OHD. Same thing for the fiber optic in terms of loading up the information, observer range, and then outputting the OD at observer range and fiber optic in OHD. For the fiber optic, we have two types of fiber. We have a single mode fiber where we want to know the mode field diameter, and then we have a multi-mode fiber where we want the numerical aperture. We'll be going through a little more of this and how all three of these are the same thing. We'll show how that works later on in a more detailed discussion. Next, we have the diffuse reflection. This again is patterned right after the ANSI standard, so we'll want to know the spectral reflectivity, and what spectral reflectivity is how much of the power or energy coming off the diffusely reflecting surface. So right now, if you want the worst case, we say, well, all the energy or power that hits the diffusely reflecting surface is being reflected off, so we'd set it at 100%. Most of the time, though, diffusely reflecting surfaces don't reflect 100%. So it depends on whether you want worst case or you're going to do a more realistic case as to what to set that at. If you want the worst case, we'll put it at 100%, and for viewing angle, worst case is 0 degrees, meaning we're looking right down the normal or a perpendicular to the diffusely reflecting surface. Most of the time you're at an angle, so a more realistic case would say, well, my viewing angle might be 30 degrees or 60 degrees. Beam on target, the default is set to 1 micron. This is so we're looking at a source type, which would be a point source or a small source. And I should mention that when we say point source, we're really talking about a point source being in the retinal hazard region, 400 to 1400 nanometers. And that's because in order for it to be a point, it has to form an image on the retina. And but outside the retinal hazard region, where we don't actually get, the light doesn't actually get to the retina, there's really no such thing as a point source, so we refer to it as a small source. Okay, so, but anyway, point source means that we're looking at something that would, if we get to the retina, is small, or otherwise it's just a small source. And so the worst case would be a small or point source type. And so we put the default at 1 micron so that regardless of the observer range, you have a point source. This section does calculate extended source automatically because it's pretty straightforward to do. And I'll show you that if we leave the observer range at 10 centimeters, and let's say we change the beam on target to 10 millimeters, you'll notice it changes to extended because this would be an extended source. If you don't know what an extended source is, then you'll have to wait till we get in discussions later on about extended sources. But I did want to point out that this section calculates an extended or point source automatically depending on these two inputs right here. And then, of course, the diffuse reflection has its own exposure duration. Lens on laser, fiber optic, intrabeam work off of this exposure duration. Diffuse reflection has its own, and that's because often when we're doing a diffuse reflection calculation, we may want something longer than the ANSI default, because in diffuse reflection, there are times when we will, particularly for visible beams, allow the beam to strike a diffusely reflecting surface, and then we're looking at the mode structure of the beam. So we may stand there and look at it longer, and we want to know, is there a hazard, and we'll want to do it over a longer period of time than, say, a quarter of a second. Maybe we want to put in something like 600 seconds. Okay. So, of course, we've already talked about what the source type is. This is the MPE associated with the diffuse reflection. And really, the reason this MPE would be different from this one is based on these exposure durations. Okay. Then we have the NHC. If we have an extended source, this will say extended source I NHC. And of course, if this is a point source, it'll say point source I NHC. Then we have OD at observer range, this range right here. We have the skin diffuse reflection NHC, the skin MPE, and the time skin MPE for the diffuse reflection. In this little box, this is radiance and radiant exposure at observer range. So the observer ranges we're talking about is the intrabeam is here. Lens on laser is here. Fiber optic, of course, is here. And this is calculating the radiance or radiant exposure in 1 over E squared or 1 over E for the beam diameters, not going through a limiting aperture. And these are very handy when we're looking at barriers, where we want to know what the irradiance and or radiant exposure is at a barrier distance. And so if somebody says, well, I have a laser and I'd like to know at my beam, I'd like to put a barrier up at about 3 meters away from the output of the laser. I'd put 3 meters in here, and then I could get my beam information here. Now I know that for some of us who are really used to this, that in the previous versions we had it at just 1 over E squared, assuming that you knew that to get to 1 over E, you just double the irradiance in 1 over E squared. But we thought we'd go ahead and fill the whole thing out, also offering a radiant exposure, which we didn't before. Okay. Correction factors, time limits, we've already seen from the menu that this can be changed, but normally you're going to want the correction factors and time limits information up here. Intrabeam, so reporting this information, these are intermediate values. So if you're doing hand calculations and your calculations differ from the outputs of what EASY-HAZ says, you can go in and look at some of these intermediate results and see if there's a difference in what you've calculated and what EASY-HAZ has calculated. Of course, if you have intrabeam up here, it's looking at all of this information here and what's over here. If you have diffuse up, then it's looking at this information, but of course still using the same laser parameters, other than you'll have different exposure durations. So in this, you can see that all of this is blue. You'll notice that this is where the correction factor C sub A is. We can click there and get C sub C. Here's C sub B and C sub G. This is alpha effective, and also the repetitive pulse correction factor CP. This is alpha X, or these are used for extended sources when we're talking about the angle subtended from the observer looking back at the source. So this is alpha X and alpha Y. Alpha max, this is alpha max for T max, meaning the exposure duration, and alpha max for small t would be if we have a repetitive pulse laser or a pulse group laser where we're looking at the pulse duration as an exposure duration. And same for CE, you have CE for T max, which is the exposure duration, and CE for T, which would be for a pulse duration if we're running a pulse laser. And then of course we have T1 and T2. In this section we have the limiting aperture used in the calculation for the eye and the limiting aperture diameter for the skin. You can click these and you can see what the area of the limiting apertures are. Okay. Right here we have the peak power irradiance and we have average power irradiance. We can click those and get pulse radiant exposure or average radiant exposure. You can see it's just a units change. Okay, and this right here doesn't work just yet. It does work, but nothing's going to happen when we click it. We'll need to get into optically aided viewing, and then we can see what goes on here. All right, so we'll wait till we get into a little more detail. This is the transmission through the limiting aperture. So it tells you the percentage of the power or energy that's passing through the limiting aperture at the observer distance or observer range. If you click here, it gives it to you in watts, and that's going to be keyed up as to whether you've entered power or energy here. It's looking at the percentage or how much of the energy or power that you've listed here is going through the limiting aperture. And then these are just laser source calculated values. This will change depending on what we have here. If we put single pulse, we get a little bit of a change on that. If we have repetitive pulse, then repetitive pulse information in terms of MPE and laser calculated values, there's some differences there. And of course, pulse groups, we get different information. So let's go over to the PDB, and we'll see that this, of course, would be where all the records are located. We'll look at this in more detail later. The menu that we have here, you can save the PDB. So if I have 10 lasers in here, say for example, I have 10 lasers in a particular area. I want all those analysis together. I can save these 10 records off as the PDB file, maybe name it what the location is or the building number, something like that, a building and room number where these, where these lasers are located. And then if I have a PDB and I want to load the PDB from file, so I want to, let's say I was working on this, they've added another laser, so I want to add that laser to the database I've already created. I would load the database, add the laser in, and then save it off again. And if I want to do the load a PDB back in from, this is the option I would select. Save parameters to the PDB file. That means if I have something over on the interface page and I want them ported over here from this page, I can hit here. If I select a record, I can use load parameters from PDB, select that record, click this option, and what happens is everything from the PDB is ported over to the interface page. We'll look at that in more detail. See if I can get that this time. There we go. We have delete records. So if I have records in here, I can delete a record. If I click on a record, I can delete that record, or I can delete all the records. I can do, well, let's do this real quick just so we can see that. Just put some information in. I'll say save to PDB. Okay. And let me try that again. Sort. I can do a multi-column sort, a 3-column sort. So if I have, when you do an audit, you may wind up with 10, 20, 30 analysis, or you could wind up with hundreds of analysis in here. And so you can do a multi-column sort where I say, well, okay, I'm going to pick a column out here, and let me cancel this. You'll notice that there's a lot of columns involved here. And I can sort this by any of the columns I want. And so in a 3-column sort, you sort the first column, and then you'll go in and you'll do the second column key, and then the third column. So I may want to sort by area, and then laser, and then maybe mode of operation. So I can do that with a multi-column sort. And then you also have a single column sort where you just say, well, I have one column, I'll tell you which column I want to sort on, and that's by highlighting that column. Let me show you how that works. Quickly I can do that. And you can go to single column. You'll see that the fact that I highlighted 5, it says, okay, I'll sort this, and you can tell it whether you want to sort by ascending or descending. And I can arrange columns. We use these column numbers and data numbers to arrange these, so I can say, well, I want different columns in 3, 4, 5, 6, 7, or 8. I can switch these out with other columns on down the stream. And that's because when I do, the reason I go want to arrange it maybe with different columns is because if I do a inventory report, it's going to print out columns 1 through 8, and that's all it's going to print out. So I may want to, depending on when I'm issuing an inventory, I may want different columns in here so I can arrange by columns and then do an inventory report. And then of course we have the navigation. Okay. That's really about all there is to the quick overview. I know that was relatively fast, but it gives you an idea of how the software is laid out. That's all there is to the software. It's, as I said, an Excel workbook. It has 2 sheets or 2 pages, the interface for inputting your parameters, and then the interface for the database. And that's really about it. So that's it for the overview, and the next videos will be going into more detail on each section. Okay, that's it.